So what we are trying to demonstrate today shows how the real graphics library is organized, which we try to study during our labs for graphical user primitives. So this conversation today sort of like prepares us for for us to look at the actual code. But before we switch over to the lab, I would like to also talk about one more feature of structures and classes in C++, which is called virtual functions, because virtual functions are very important for program design that is relying on inheritance between classes, like we try to demonstrate over here. So let's just say that I want to have a function in in our system. I'd like to have a function, and I'll just declare it somewhere or define it somewhere, because I'm using just like a little file for this very quick demonstration. Avoid the print. I'd like to be able to print triangles, right? Triangles, and I'd like to be able to print call the print function. So I could easily make a function that looks like this. Circle okay, so that is a member function of circle. Once again, so instead of going directly to print circle right here and print triangle here, let's switch over to this type of arrangement for the sake of our demonstration. And so for both triangle we can have these functions. These will be our function names are overloaded because print and print over here is the same. Their difference will be checked by the compiler by looking at their parameter list, and so therefore, this is something that compiler permits to overload functions with the same name based on their parameter list. That's not the problem. And so I will change this part of our program to, say, print, and use it like this. Essentially, trying to use function print to print both of these shapes. Let's build it and see how this works. Okay, so this works exactly the same way. Not much has changed, but now we're delegating the actual printing to our function print. One quick observation that print is a function declared inside both triangle and circle, and these are constant functions. So it would be possible, perhaps, to instead of using value parameter for circle and triangle, which makes a copy of the original circle and triangle when we call these two functions, it would be nice to prevent constructing their copies. Instead, just passing references. So it's very typical when we use objects as function parameters, that we use them as references. So switching to references is kind of simple. You just add an ampersand after the name of the type of the parameter, and so this no longer will make a copy of the original triangle when we call this function. Instead, the address of the original object will be used inside the function. And now we can rebuild this, right? So this works fine. I would also say that since this function is constant, declared constant inside both triangle and circle structure, I would probably typically also make references here constant also, because this is just printing, not intended for any kind of changes. So this would be standard function signatures. And again, remember that the promise of inheritance is that we need to, or we would like to avoid any sort of duplication. If there is something common between two different objects, commonality could bring us to the idea of inheritance. Inheritance provides common part, and we can leverage that in our program design. Besides data members, which we can share through the base class, we can also use it for commonality between commonality between functions. So, for example, here I begin to observe that both circle and triangle have the same kind of function named print. Instead of using these types of functions, which I will right now probably just comment out to make sure that we're no longer using them. It would be possible to replace two functions, which is probably a desirable thing, with a single function. And of course, it will be taking a shape as a type. So this is going to be a shape. And the idea behind it is that we're going to use this shape to call the print function on both types of object. So this would be basically, the idea would be that we would like to use the same types of calls on the client side inside of our main function here. But on the implementation side, we would like to avoid duplication of these prints for circle and triangle, because circle and triangle already related and they have a shape as a base class. We would like to be able to do something like this. However, if we scroll to the shape, shape does not have a print function. In other words, if I try building it, okay, it just simply complains that print is not a member of shape. Well, it's reasonable. Print indeed is not a member of shape. So what we need to do is that we have to basically take signature of this function with its return type, the name of the function, and the const qualifier over here. And we need to add it over here as a function declaration. Right, so function declaration or function prototype simply requires a semicolon. And this is true because we simply don't know what kind of print we need. Shape has to know what type of object it is part of in order to be able to invoke the right print. And to be able to resolve this dynamically, we have to qualify this function as virtual. So once we make this qualification, that there is a function print that belongs to both circle and triangle, it's possible to basically use shape, which is a base class, to delegate print calls and other types of functions just simply based on their names to the underlying circle or triangle. So let's see. So this is now is in place. I added this virtual print. Virtual because it doesn't exist at this level. However, at the level of the circle and triangle, the actual implementation does exist. And of course, it does its own thing. So now, look, the multiple copies of print function at the global level are gone, instead replaced by a single function that takes our shape and uses this shape to print, and the print supposed to still show correct information for each single object. Let's give it a try. Build. 1 second. Shape color cannot convert argument 1 from int to const shaped reference. Okay, and this is happening part of this. So it basically just wants us to have a constructor over here when we pass objects by reference. So that's okay. I will add constructor. Shape constructor takes integer color, and we can construct color from color like this, and this is shape constructor. Let's build this. Now I'm getting shape print. Oh yes, because I'm defining this function without any definition, I actually have to explicitly say that this virtual function will be pure. So I need to do something like this, and this makes a function pure virtual function, which, let me comment here, pure virtual function does not require a definition. So the definition that will be used at runtime for corresponding objects that derive from this shape. All right, so let's make this change and build it. So this works. Let's find out how this runs. We still get the same output, which is nice. And again, the idea is keeping an eye on avoidance of any sort of duplication whenever possible by taking advantage of what comes with inheritance. So inheritance comes with the fact that we can take new data types and make them subclasses or derived classes of the base class, like our shape class. So that's one advantage, and then automatically at runtime, the shape becomes part of either circle or triangle. This is just fine. This is done simply by taking the shape definition and making it part of our of our derived classes. But additionally, it's possible to add virtual functions, and virtual functions simply need to be declared at the base class level. And then it's possible to use references of this type and call this function, and this call will be delegated to the specific kind of shape that was used to pass this information. So let's just like move this down here. And specifically, when we call print with the circle being the parameter of this function print, the shape is, of course, is the circle. And dynamically at runtime, compiler will decide that we will call circle's version of print. And the next time we call print with the triangle object, so of course this shape is the triangle shape, and this time when we use the shape to call print, it will invoke triangle's version of print. And this is why we're getting these two different outputs, calling the same function twice, but with two different objects. And the outcome, again, is that this print gives us the output that first time it's for the circle, and the second time it's for the triangle. So this set of features with class inheritance in C++ or structure inheritance in C++ is called dynamic polymorphism, kind of fancy word for it. So this here is using dynamic polymorphism. Like this. And so this is a feature, this dynamic polymorphism is based on the fact that a function here is being defined as, rather declared as virtual. So let's make another quick demonstration of what is happening at runtime and how is everything resolved at the runtime to make these concrete functions inside triangle and circle be invoked with respect to the specific object that was passed to this function, which is sort of like interesting that the specific type is basically removed over here, but because the function is virtual, it is still invoking a specific type of objects function. So let's just do a quick demonstration of this in this segment. Right, so I'll just open yet another copy of my Scratch pad over here. So basically we construct two objects, a circle and a triangle. Okay, and both of them derive from a shape. So there is a shape, and shape in itself is an object because it has color inside, and it could have additional elements inside. I try to make it visible in this 2D space like this. And then we have two of them. We create circle and triangle. And so we'll take essentially two copies of this. And we'll say that the circle over here and triangle over here are the objects that contain shape inside of them, because we have this inheritance in place, right? So we have this. In fact, let me just duplicate what I already have. So we have two different object types, and one of them is a circle here. Another one is a triangle. And both provide the function named print. We know that both provide their own custom version of print. Print is a function that does something specific. So just to show that there is print in both triangle and circle. So this right, so this is a function over here that we have, and this is another function over here. I'll just try to kind of highlight them in different colors, right? So this color and some other shade over here. So these are the two different functions, because one is designed for the circle and the other one is designed for the rectangle. And yet we have a global function named print. Global function named print, which takes shape reference. So this is our global function named shape over here. And so when we try to call print using this shape, right? So we get this reference inside this function. It's called shape, right? So this is a reference. To object. The first time this reference is pointing to the shape inside the circle. The second time it's pointing to the shape inside the triangle, like this. But the thing is that because this function print was declared virtual, this guarantees that when we call print using the shape which is part of the circle, the actual code is delegated to the specific function implementation, which is specific to the circle. And likewise, this call really is diverted or delegated to the print provided by the triangle. And so this is happening because we're passing specific types of objects, a circle and triangle. So just remember that this kind of like this behavior is what we say dynamic polymorphism. This dynamic polymorphism behavior is done reference to the base class, which then allows to invoke specific print functions that are part of circle and triangle. But notice that the original call is made through the base class and reference to the base class and not a specific object type. So this is a feature called dynamic polymorphism. Of course, this is also being discussed part of our agenda in chapter 13 of the book. So just use this prototype for your advantage when you're reading the chapters. And so now that we've got this demonstration in place, let's switch over to our continuation of lab 2. But this time, instead of just copying and pasting samples of the of the lab as we did a week ago, this time when we start using the real shapes and the real graphical primitives in our presentation of lab 2, we'll be examining the actual underlying code and pointing out what is happening and how things work, how everything is put together.